In this lesson, we're going to talk about electron configurations. And electron configuration refers to the assignment of electrons to the different subshells. And so here's an example of an electron configuration, 1s2, 2s2, 2p1. What this means is we're talking about an atom or an ion that has 5 electrons. This number 2, 2, and 1 here refers to the number of electrons. And in this particular atom or ion, we have 2 electrons assigned to the 1s subshell, 2 electrons assigned to the 2s subshell, and 1 electron assigned to the 2p subshell. Now, when we write electron configurations, we may omit the superscript, and if that's omitted, okay, then that is implied to be 1. So, for example, 1s2, 2s2, 2p1 can be written as 1s2, 2s2, 2p, okay? So, based on that information, which of the following can have an electron configuration of 1s2, 2s2, 2p1? Lithium with a -2 charge, boron, or carbon with a +1 charge, or is it all of the above? Well, let's take a look at this. This electron configuration refers to something that has 5 electrons. 2 plus 2 plus 1, that's 5 electrons. So it can refer to an atom or an ion that has 5 electrons. Lithium, atomic number 3, has 3 electrons, but the -2 charge, that means 2 more electrons, so that's 5 electrons. Okay, so it will work with lithium. What about boron? Boron, a boron atom has 5 electrons, so it will work with boron as well. Carbon, atomic number 6, so 6, and then the +1 charge means 1 electron gone, so that leaves 5 electrons. So carbon with a +1 charge will also have 5 electrons. Okay, so the correct answer to this one is all of the above. All of these species here, the monatomic ions and the atom, have 5 electrons in them. Okay. We use the word ground, okay, to refer to the most stable configuration. So the ground state configuration refers to the most stable or the lowest energy configuration of an atom or an ion. And the word excited refers to higher energy condition. So an excited state configuration would involve one where the atom or the ion is at a higher energy. Okay, so which of the following is the ground state configuration of hydrogen, and which one is an excited state? Let's look at the choices. 1s1, 1s2, 2p. So this one says you have an electron in the 1s orbital. Okay, this one says you have 2 electrons in the 1s orbital, and this one says you have 1 electron in a 2p orbital. Well, obviously B can't be right because hydrogen has only 1 electron, right? So in which orbital does the hydrogen atom have, does an electron of the hydrogen atom have to be if it were to have the lowest possible energy? If you recall from an earlier lesson, we said that E, the orbital energy, is just depends on the quantum number n, so it's -r sub h z over n squared, right? Where z is the atomic number. So the lower the n, the lower the energy. So an electron in the 1s orbital would correspond to a lower energy. So this would be the ground state of hydrogen. That would be the ground state configuration. And 2p, an electron in a 2p, would be an example of what we would call an excited configuration, an excited state. Okay, so an atom of hydrogen where its electron is in the 2p orbital would be a high energy atom. Eventually that atom is going to lose that energy, give it off in the form of light, and the electron goes down to the 1s orbital, we might say. Okay. Now, unless otherwise specified, when we talk about electron configuration, for much of what we're going to be doing in this lesson, when we talk about electron configuration, we mean the ground state configuration. So, unless it's unless it's obvious from context that we're not necessarily referring to the ground configuration. When we say electron configuration, we mean the ground state electron configuration. Let's try an example of an excited configuration. Let's look at helium, for example. Helium has 2 electrons. So that means the ground state configuration for helium, you can get that by putting those 2 electrons in the 1s orbital. Okay, so this would be your ground state configuration. Any other configuration of helium would be an excited state. So if you put, for example, 1 electron in the 1s orbital, and the second electron you put it in the 2s orbital, this would be an example of an excited state. What's another example? You can put 1 electron in the 1s, another electron in the 2p. That's also an excited state of helium. That's another example. You can put 2 electrons in the 2s. That would be an excited state. Okay? So those are excited state examples of excited state configurations of helium. How do we come up with the ground configuration for an atom? What we do is we assign electrons to the lowest energy orbitals. Okay? But we just can't pack them all into the 1s orbital because there is a restriction. Okay, Pauli's principle says you cannot assign more than 2 electrons per orbital. So typically, to get the lowest energy configuration, the ground configuration of the atom, you pack the electrons into the lowest possible energy orbitals, and the order in which you fill those orbitals depend on the value of n plus L for the orbitals. The lower the n plus L, okay, the more if you put electrons in orbitals with lower n plus L, you attain a lower energy for the atom, typically. Okay, so for a typical atom, the sequence of filling of the orbitals the orbitals follows n plus L. Okay, so if you have 2 orbitals that have the same, or 2 subshells that have the same n plus L, then you filled the subshell with the lower n first. Okay, this procedure for coming up with the ground configuration is known as the Aufbau principle, or the building up principle. So before we do that, let's just clarify. In a typical atom, in which of these orbitals would an electron have a higher energy? Then you go by n plus L, right? So n plus L for 3p, for a 3p orbital, n is 3, and remember L is a code for S, P, D, and F is code for the quantum number L. If L is 0, you're dealing with an s orbital. If L equals 1, you have a p orbital. If L equals 2, you call that a d orbital. If L equals 3, you call that an f orbital. Okay, so a p orbital would have L equals 1, so 3 plus 1 would be 4. Let's look at a 3d orbital. N is 3, and for a d subshell, for a d orbital, L is 2. Okay, so 3 plus 2 is 5. And then for 4s, N is 4. And for an s orbital, L is 0. Okay, that's 0. That gives you 4. So, in which of these atoms, in the typical atom, in which of these orbitals would an electron have the highest energy? The answer would be 3d. Okay. Here's how you can use the periodic table to remember the typical order that subshells are filled, or orbitals are filled in an atom. You start with 1s, and then 2s, and 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and then 7f, and then 5d, and then 6p, 7s, and then it will be 5F, and then followed by 6D, and then 7P. Okay? All right, so one thing you'll note about this is that if you look at this block right here, which we call the P block, this is the right side of your periodic table. If you count the number of columns here, there are 6 columns here. This is columns 13 through 18, okay? And if you remember, the most number of electrons that you can put in a p subshell is 6. For each p orbital, you can put 2, but p orbitals come in sets of 3. So you can have as much as 6 electrons in a p subshell. And so that's a good way to remember that there's 6 columns on that part of your periodic table. If you look at this block right here, there's 2 columns right here. You call this the S block. Okay, this is the P block, by the way. That's the P block. That part of your periodic table is called the P block. This part of your periodic table right here is called the S block. Okay, you'll notice it's 2 columns. Okay, over here in the middle, if you count the number of columns here, look at this. This is from column 3 to column 12. That's 10 columns. Okay, a good way to remember that this is the D block is that in a D subshell, you can put as much as 10 electrons. Okay, and for an S block, then the most number of electrons you can put in an S subshell is 2. So a good way to remember that these 2 columns here represent the S block. Is the most you can put in an S subshell would be 2 electrons. And if you look at this one, you'll notice that this F block consists of 14 columns. The most number of electrons you can put in an F subshell is 14. So let's look at an example here. What's the electron configuration for scandium? The way you would do this is you'd say, okay, it's 1s2. Okay, the first 2 electrons will go in the lowest possible energy orbitals. That would be the 1s. Then the next electrons will go to the 2s or 2s subshell, and you can put 2 electrons there. And then the next one would be 2p. That allows you to put 6 electrons there. So that takes care of 10 electrons so far. 2 plus 2 plus 6, that's 10 electrons. Okay, how many more electrons do we have to fill in to account for? So yeah, you're dealing here with 10 electrons so far. And scandium has 21 electrons. So you get 11 electrons more to go. So the next subshell that can hold electrons would be 3s. You put 2 electrons there. That makes 12. And then 3p, the most you can put in a p subshell is 6. So that takes care of another 8 electrons, or up to 18. Up after 3p, you put the next 2 electrons in the 4s. That gives you 2 more electrons. So that's 10 plus 8 plus 2. That's 20 electrons. Then the next electron will go in the 3d subshell, so 3d1. So your electron configuration is this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. That accounts for the 21 electrons of scandium. All right. Now, if you look at neon, what's the electron configuration for neon? It's 1s2. Okay, if you were to write it, you'll find that it's 1s2, 2s2, 2p6. Okay, so 1s, 2s, 2p. So that takes care of 10 electrons. So sodium, which is 1 more electron than neon, would be 1s2, 2s2, 2p6, and then after 2p comes 3s. So 3s1, okay, after 2p6. Now, it's customary to abbreviate the electron configuration by abbreviating the first part up, okay, using what's called the noble gas core notation. So here, since 1s2, 2s2, 2p6 is the electron configuration for neon, for sodium you can abbreviate 1s2, 2s2, 2p6 by using the symbol for neon enclosed in square brackets. Okay, so so electron configuration for sodium would be neon core 3s1. Okay, let's look at some patterns in electron configurations. What you'll find if you examine electron configurations is that the valence shell, okay, that's the largest N, okay, valence means outermost electrons, those are the electrons with the largest N, will be corresponds to the row in the periodic table where the element belongs. Okay, so the valence shell for the elements in the first row is 1. Elements in the second row, the largest N you'll find for the occupied orbitals would be N equals 2. And for the third row elements, N equals 3, and so on. And one thing you'll also find is elements belonging to the same column, they'll have the same valence configuration. Valence configuration means the configuration for the largest N, the outermost shell. Okay? And there'll be, that's one thing the elements in the same column will have in common. So let's illustrate that. If you look at the electron configuration for the noble gases, helium is 1s2, neon is 1s2, 2s2, 2p6, and look, we're abbreviating 1s2 here by using the noble gas just before neon, which is helium. That's 1s2, that's a helium core. And then argon right here has a neon core, and then after that 3s2, 3p6. Krypton will have an argon core, 4s2, there's a 3d10 and 4p6. What do all of these have in common? They all end with s2p6. Okay, except for helium, which only has 2 electrons, it ends with 1s2. It is 1s2. Argon ends with 3s2, 3p6. Krypton has an s2p6. So all of these have completely filled outermost. That's what valence means, outermost S and P subshell. So xenon, what's the last thing you're going to write if you were to write the electron configuration for xenon? You're going to say 1s2, 2s2, and so on and so forth. Based on the pattern here, you'll see the last thing you'll have to write is 5p6. Look at neon right here. Neon is row number 2. Okay. The highest N, the valence N for neon is 2. Argon is in the third row. The highest N for argon is 3. The valence shell is a third shell. Krypton is in the fourth row. The valence shell for krypton is 4. Okay, and so for xenon, the valence shell would be 5. Let's take a look at the S-block elements, and let's try to understand why they're called the S-block elements. If you look at hydrogen, electron configuration is 1s1. Lithium, okay, comes after helium. So after helium, the next orbital would be 2s, so 2s1. So you can see the valence shell is the second shell. Sodium comes after neon. So after neon core, you fill in your 3s orbital. So this is the third row. Outermost shell has a 3s orbital with 1 electron. So what do you think potassium is going to be? Potassium comes after argon. So it's going to have an argon core, okay? And then potassium is in the fourth row. After the argon core, the next subshell to be filled is the 4s. So argon core 4s1, okay? Rubidium comes after krypton. So 1 more electron than compared to krypton. So it's going to have a krypton core. And then the next orbital to be filled would be the 5s orbital, so 5s1. So this is row number 5. And then cesium comes after xenon, so it's going to have a xenon core. And then after that, 1 more electron. That extra electron is going to be in the 6s orbital. So what do you notice? What do all of these have in common? Their valence configuration, we say, is ns1. Okay? Let me write that. ns1. So the valence configuration for these elements is ns1. What do you think the valence configuration for these elements are going to be? Group 2a. 1 more electron, so the valence S electron can accommodate 1 more electron. They can accommodate up to 2 electrons, so you would expect all of these to have a valence configuration of ns2. Okay? So beryllium comes after lithium. So if lithium is helium core 2s1, beryllium is helium core 2s2. Magnesium, okay, let's see. Magnesium comes after sodium. So if sodium is neon core 3s1, then magnesium is neon core 3s2. Calcium comes after potassium. So it's going to be neon core, and then it's in the 4th row, so 4s2. Okay, strontium comes after rubidium, so strontium would have argon core instead of 4s. I'm sorry. Oops, I got it wrong. Calcium would have an argon core 4s2. And then rubidium is going to have, strontium is going to have a krypton core, and instead of 5s1, we got one more electron, that's 5s2. And then barium, okay, instead of 6s1, it's going to have 6s2 as the valence configuration. So that's what they all have in common. And that's why these elements right here are known as the SBlock elements. Similarly, if you look at the DBlock elements, you'll find that for scandium, we've done scandium earlier, the last thing you write is D1. Okay, so 4s2, after 4s2, 3d1. So you can see the pattern. For titanium, the next one's going to be D2. So that goes all the way to D10. So if I have to do for zinc, what would it be? Zinc would have, okay, the noble gas just before it, argon core, and then 4s2, and then 3d10. Okay, what would it be for manganese? Manganese is over here, so this is d1, d2, d3, d4, d5. So manganese will have an argon core, 4s2, 3d5. Okay, now what about yttrium down here? Okay, that comes after, so you go back, it comes after krypton, so it's going to have a krypton core, and then you're 1, 2, 3, 4, 5, you're in the 5th column now, so 5s2, I mean 5th row, 5th period, 5s2, after 5s comes 4d, remember this is 3d, the next row is going to be 4d. So 4d1. Okay? And then zirconium after that is going to have 4d2 and so on. Okay, what about the p-block elements? These are the p-blocks. Okay. Alright, so boron would be helium core. Okay, and then 2s, 2, and then 2p1. Okay. So you can expect aluminum would end up with 3p1, and then this is going to end up with 4p1. So this is, all of these would end up with p1. Okay, the valence configuration would have, the valence subshells would have 3 electrons total, 2s2, 2p1, that's 3, and that's part of the reason why, that's the reason why it's called group 3a. Okay, the valence s and p subshell here for this column 14 would have 4 valence electrons, because this is going to end up with P2. So carbon would have, for example, a helium core, okay, and then 2s2, 2p2. So you're looking at 4 valence electrons for carbon, okay, 4 outermost electrons. In the outermost shell, the largest end, there are 4 valence electrons. So you have P2, and this is going to be P3, P4, P5, and then this group right here, P6. Remember, helium is just 1s2. Okay, so that's how you come up with, so that's the pattern in the electron configurations. let's apply that. Which atom has an electron configuration of 1s2, 2s2, and so on, ending with 4p5? Well, just p1, p2, p3, p4, p5. So it's one of these, right? And then the highest n, oops, the highest n is 4. So row number 1, row number 2, row number 3, row number 4. So it's in row number 4. So what element is in row number 4 and has an electron configuration of 4p5? The answer would be bromine. Okay, if you want to write that completely, you would say it's got an argon core, the noble gas before it, and then followed by 4s. So you can put 2 in the 4s, and then followed by 3d. You can put 10 in the 3d subshell, and then 4p5. Okay, let's count the electrons there. Argon core has 18 electrons, plus 2 electrons in the 4s, plus 10 electrons in the 3d, plus 5 electrons in the 4p. That's 20, 30 plus 5, that's 35 electrons. Bromine has an atomic number of 35, has 35 electrons in a neutral atom. Okay. Which of the following is not a valid configuration for a lithium atom, which is 3 electrons? 1s3, 1s2, 2s1, 1s2, 2p1, 1s1, 2p1, 3s1. Right here, immediately say that that can't be right. So this is the correct answer. Okay? It's not valid. What's wrong with 1s3? You remember an s subshell is just an s orbital. So it can hold a maximum of 2. Okay? Maximum for an s subshell. A p subshell can have a maximum of 6 because it's actually 3 orbitals, and you can put 2 electrons in each orbital. And a d subshell can have a maximum of 10. All right, so what about 1s2 to s1? That's going to be the ground state, right? So why aren't these other two wrong? Why are these valid? Well, as long as you're not violating Pauli's principle, okay, you're not putting more than 2 electrons in an orbital, or you're not implying that there are more than 2 electrons in an orbital, then you're fine as far as your electron configuration is valid. So this is a valid electron configuration. It just so happens to be what we would call an excited state. This will not be the most stable form of lithium. Okay? And 1s1, 2p1, 3s1, the same thing. So these are all valid because they have 3 electrons. Lithium has 3 electrons. So 1, 1, and 1, that's 3 electrons. 2 and 1, that's 3 electrons. So it just so happens that these are excited states. Okay? Let's take a look at this one. In a typical atom, which of these orbitals is filled last? Okay, so you go to your pattern. You go to your sequence. So it's 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, okay, and then 5s, and then 4d, and then 5p, and then 6s, and then you do 4f, and then 5d, and then 6p, and then 7s, 5f, 6d, and then 7p. So, okay, so 3p is over here, 3d is over here, 4s is over here, and 4p is over here. So 4p is the orbitals that would be filled last in a typical atom. Okay. Which of the following is the ground state configuration of sulfur? Sulfur is right here. Okay, so it's in the 3rd row. So you know that the ending is going to have the highest end is going to be 3. 1, 2, 3, 3rd row. And this is in the fourth column of the P block, P1, P2, P3, P4. So the last thing we have to write is a P4. Okay, so it can't be this, it can't be this, and it can't be that. And let's just verify. You have 16 electrons. 1s2, 2s2, 2p6, that's 10, plus 2, that's 12, plus 4, that's 16 electrons. Okay. Now, there's other things you can look at here too. You can see 2d6. There is no 2d orbital, so immediately you know that that's wrong. That's about there is no 2d orbital. Here, you'll notice there's a 2p7, so immediately you can spot that. That can't be right. You can't have more than 6 electrons in a p subshell, right? And if you add up the electrons here, you're going to end up with 18 electrons. This would be the ground state for argon. All right, which of the following is the ground state electron configuration of aluminum? Well, aluminum is over here, so it's in the P block, right? And 1, 2, 3, so third row. So 3p1 is the last thing you're going to write. Well, they're all 3p1. So what's the correct one? Well, let's construct it. What's the noble gas just before it? Neon. So you have a neon core. Okay, and once you get to start with the third, once you get to the third row, the next orbital would be 3s. So 3s2, and then 3p1. So the correct one is this one. Up, yeah, neon core, 3s2, 3p1. Which of the following is the electron configuration for zirconium? Zirconium is over here, number 40. So that's D1, this is D2, okay? And so this is the fourth row, so this is 4s, and then 3d, and then 5s, and then 4d. So it ends with 4d2, okay? 5s2, 4d2. The element, the noble gas just before it is in the fourth row, which is krypton. So it's got a krypton core, 5s2, 4d2. Now, an electron configuration tells you how electrons are distributed among the subshells, how they are assigned to subshells. If you want to provide a little bit more detail, you can draw what's called an orbital diagram. This one specifically says how electrons are assigned to the orbitals. Okay, and in an orbital diagram, you use arrows to represent electrons. An electron with a spin of +1/2 or spin up would be represented by an up arrow. An electron with a m sub s of -1/2 or spin down is shown with a downward pointing arrow. When you construct your orbital diagram, you must make sure you follow Pauli's principle, which means no more than 2 electrons per orbital, and if there's a pair of them in an orbital, one has to be spin up, the other has to be spin down. Okay, so let's look at 1s2, 2s2, 2p4, that electron configuration. Okay, what would be an orbital diagram you can draw for that? So 1s2 means you have 2 electrons in the 1s orbital, so I have one spin up, the other one has to be spin down. Okay, 2s2, 2 electrons in the 2s orbital, so that's 1 electron spin up, the other electron spin down. And then 2p4, that means 4 electrons in a 2p subshell. Now, anytime you have a partially filled subshell, okay, in this case you'll notice your p can accommodate up to 6, right? But you only have 4 electrons. So you'll find that there's more than one way of assigning electrons to the p subshell, those 4 electrons. In fact, there's 15 different ways you can do this. Here's one way. You can go 1 up, down, that's one way. Okay, another way would be 2 here and these 2 here. So you can have up, down, so that's another way. And then another way would be something like you can 1, 2, 3 all spin up, and then the fourth one would be spin down. And so that's another way. Okay, so there are many ways of doing it. Anytime you have partially filled subshell, you'll typically have more than one way of drawing an orbital diagram. Also, an orbital diagram, you don't need to use boxes, so you can just put line up your, or set it up like as a row of lines. So 1s, 2s, and then 2p would be 3 orbitals, so you're represented by 3 lines. So you can do it this way. So you can say there's one orbital, a pair of electrons in the 1s, a pair in the 2s, and then you can say 3 with parallel spins in the p subshell, and then a fourth electron spin down in the p subshell. Okay, so this is another way you can draw that orbital diagram. Now, Hund's rule of maximum multiplicity says that you can get the lowest energy assignment of electrons if you fill the sublevel singly first with parallel spins before pairing them up. In other words, if you have a partially filled subshell, okay, remember we said there are going to be more than one way of distributing the electrons of partially filled subshell. Well, Hund's rule says not all of those ways would correspond to the lowest possible. Some of those ways would actually correspond to a lower energy assignment of electrons, so it will give you a more stable atom. And the one that has the lowest energy is one where you spread them out first. You spread out the electrons first with parallel spins before you pair them up. Okay, so in the case of oxygen, ground state 1s2, 2s2, 2p4. So you have a pair in the 1s, one spin up, one spin down. By the way, there's nothing wrong with drawing it spin down first and then spin up. As long as you don't violate Pauli's principle, it's okay. But this the convention is to just start with spin up and then go spin down. It doesn't really matter. And then 2s orbital, you can go one spin up, one spin down. That's 2 electrons. Okay. And the p4, according to Hund's rule, to get the maximum multiplicity, maximum multiplicity simply means you get the maximum number of unpaired electrons. You spread them out with parallel spins before you pair them up. So for these 4 electrons would be distributed this way. Spin up, spin up, spin up, spread them out, and then pair. Okay? That's one way. Okay? So that's one of those 15 ways. It's not actually the only way you can do it. You can, like the fourth one, for example, you can put that fourth one over here. There's nothing wrong with that. Okay? That's also, this is one, each of these different ways is called a microstate. So this particular microstate is one of those that have maximum multiplicity, the most number of paired electrons. Okay? And so you can have the pair over here instead. Or you can flip those spins. You can have spin down. You can have, for example, spin down, spin down, spin down, and then pair up over here. Okay, so that as long as you have the maximum number of electrons with maximum number of unpaired electrons, you have maximum multiplicity. And like I said, the customary way of doing this is to start with electrons spin up first, spread them out, and then put the next electron spin down, start pairing them up after you spread them out. Okay, so how can we write an orbital diagram for the excited state of oxygen? Well, that would have to be 1s2, 2s2. Okay, one way would be 1s2, 2s2, and then instead of 2p4, you can have 2p3 and 3s1. That would be, so you can have spin up, spin up, spin up here, and spin up there. One way, that's just one of many, many ways of doing it. So those are the excited states. Okay, so this is an example. Right. Now, how many electrons are unpaired in the oxygen based on what we've talked about so far? Oxygen, you say, has a P4 outermost configuration, right? So this is P1, P2, P3, P4. So you have a partially filled subshell, a P subshell, and there's 4 electrons in there. The most number of electrons you can have would be, most unpaired electrons would be 2. 3 of them, you spread them out 3, up, 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 and then the 4th one would be spin down, would pair up with the first one. So you have 2 unpaired electrons in the ground state. Ground state means the lowest possible energy state. So that's 2 unpaired. Okay. Now atoms that are affected by magnets, magnets are called paramagnetic, and those that are not are called diamagnetic. And the explanation for paramagnetism has to do with unpaired electrons. So anytime you have unpaired electrons, so that means atoms with partially filled subshells, you will have an atom that's paramagnetic. So to explain why nitrogen is paramagnetic, here's nitrogen right here. It's in the P1. So P1, P2, P3. So the valence configuration, the outermost configuration of nitrogen, is P3. It has unfilled, half-filled P subshell with three electrons. So those 3 electrons would spread out among the 3 orbitals, and they'll have parallel spins. So that's what makes nitrogen atom paramagnetic. Why are beryllium atoms not paramagnetic? Let's look at beryllium. Beryllium's over here. Okay, so what's the electron configuration for beryllium? Helium core, and then second row, that gives you 2s2. Okay, so your orbital diagram for beryllium, you have 1s, 2s, paired up in the 1s, paired up in the 2s. You have no unpaired electrons. Beryllium is not paramagnetic. So you can generalize this to say that all these atoms with an s2 valence configuration are not paramagnetic. And so anytime you have completely all the subshells, all the occupied subshells are completely filled, you have an atom that's not paramagnetic. Okay, so anything over here would be not paramagnetic. The noble gases will, noble gases would be further out here. Okay. The noble gases would also be not paramagnetic. So which of these is not paramagnetic? Sodium, magnesium, carbon, or titanium. You look at your valence configuration. This is P2, so that's 2 unpaired electrons in a P subshell. The valence configuration for sodium, obviously 11 electrons. One of them has to be unpaired, right? So this is neon core, 3s1. So you have that 1 unpaired electron in the 3s orbital. Titanium, okay, that's an argon core, 4s2, 3d2. Okay, that d2 is partially filled. If you remember, d orbitals can accommodate up to 10. So there's many different ways of distributing those 2 electrons in the d subshell. Okay, d subshell can accommodate up to 10 electrons. So that's also partially filled. So these are paramagnetic. So sodium's paramagnetic, carbon's paramagnetic, titanium's paramagnetic. The correct answer is magnesium. Okay, column 2A, and like I said, column 2B, or group 12, and the noble gases, those are your atoms that are not paramagnetic.